So I'm gonna kind of go fast. We got a lot to do on the new stuff today, but I know that these intersections of surfaces to form a space curve, they're kind of there's like all different, right? So there's not one cookie cutter way to solve these problems. So this one, you have paraboloid. And then you have a plane cutting through that. Now, the question is, does it cut through at a shallow enough angle so that, in x and y, you'll get some kind of circle or ellipse? Or does it cut through at a sharp angle like this that you won't get a circle in x and y? You get like some type of parabola shape that it cuts. Does that make sense? So what's going to tell us, how do we know which it's going to be? Well, the equations, right? So when we start working on the equations, then we're going to find out if their intersection is going to be circular or sharp enough. But actually, the big hint here is going to answer that question also, right? So without this hint, we wouldn't know if we've got like the red case, right? The red case, which is going to give us something like this, or the blue case, which is going to give us, something like this in space. Does that make sense? But the hint is kind of indicating it's going to be the red case, right? They're saying you're going to parameterize a circle using sine and cosine. Okay? So let's see that play out. So basically, we've got z equals x squared plus y squared, and 9x minus 6y plus z minus 8 equals 0. So if we want to figure out all the points that those have in common, then we're going to combine those equations together. And we're mostly interested in what we have in x and y. Do we have something circular in x and y or not? So that means we could eliminate z, or in other words, if this is z, then we could take that and plug it in here and see what happens. So then we're going to get x squared plus 9x. I'm going to change it around as I do it. Y squared minus 6y equals 8. So I plugged in x squared plus y squared plus z, and then I just combine x's and y's and move the 8 over. Is that okay? All right, so what is that? This is going to be a circle. We need to complete the square. So take half and square it. So half of 9 is 4.5, or 9 halves. And when we take half of it and square it, and then add that, so we're going to add 81 fourths. And then for this one, we're going to take half and square it. We're going to add plus 9, right? And then we have a perfect square, which would be x plus 9 halves squared. And we have another perfect square, y minus 3 squared equals 8. But then whenever we add on the left side, we got to add on the right. So plus 81 fourths plus 9. So we have a circle with center -9 halves 3, and radius equal to the square root of whatever all that is added up, right? This is r squared. This is all this here would be r squared. So add that up, take the square root, and you get the radius. Okay, so then that means that we are going to use sine and cosine in the x and y coordinates. So that means that x is going to be, so we could say x is going to be based on cosine, and y is going to be based on sine. So meaning that when we look down on this thing, the intersection that we're going to see is going to be a circle with an offset center offset from the origin. Why? Because it's actually making an ellipse. It's making an ellipse. The intersection is going to be a red ellipse. But if you look straight down on it, you're going to see a circle. You're going to see a circle, and how do we know that? Because we got the equation of a circle in x and y. But that center of that circle is not going to be at the origin. It's going to be offset. So then how do we do that? So to get the radius that we want, we're going to, whatever the radius is, we're going to multiply it by cosine t. And then to get the offset right, so what? The center's at -9/2. So we're going to subtract 9/2. So remember, when you're actually writing the x-coordinate, if you want it further to the right, you're going to add. And if you want it further to the left, you're going to subtract. It's when you're writing x as a function that you would add to move it left and subtract to move it right. Or in this case, subtract to move it up. But when you're actually writing what x equals, then if you want it further to the right, you're going to add. And if you want y up 3, you're going to add 3. Okay, so whatever we got here for r squared, you take the square root, that's going to be your coefficient on cosine and sine. And then your offset is going to be by the amount of where the center is, right? So we want to go left 9/2, and we want to go up 3. So that will be our x and y. And then z we can just find by using this equation. Plug in the x that we just found here, plug in the y that we just found here. Now those are both in terms of t, and then you can solve for z in terms of t. So it'd be 8 minus 9 times this x plus 6 times this y. And that will be your z in terms of t. Okay, so I talked through it fast. But hopefully, because you thought about it and worked on it, that answers any questions. But ask if do you need any further clarification on this one? So whenever you have a projection in one direction, the projection of the intersection is a circle or an ellipse. That's your cue to use cosine and sine in those two variables. Use cosine and sine. Yes, please.
If that hint wasn't given, how would we tell which of the planes to use?
Right, because of this. So you're still going to put z in there, and you're going to get this, right?
Yeah.
And then you know. So this is the equation of a circle in x and y. Therefore, cosine and sine. But like in the example I did in class last time, we did that. We did a similar thing, and we got a parabola. We didn't get a circle. Do you remember that one? Yeah, so it just depends on what you get in terms of those two variables. But so like the equation last time, we got a parabola, so we just stick with a parabola. And so we're not going to, so there you're not going to use, if you don't have a circle in any projection, then you're not going to use sine and cosine, and you're going to strategically look for which variable to assign t, and then work the other two variables in terms of t. Okay, just briefly talk about this one. Equation of a tangent line, where is it? Equation of a tangent line. So it's asking for the equation of a line. So you say, oh, I know all about lines. I'm really good at lines. What do I need to write the equation of a line? So a point and direction vector. So if they're asking me to write the equation of a line, which they are, then all the information in this problem has to be able to give me a point on the line and a direction vector. So now this information, the point and direction vector, are going to come from this curve. So in this problem, they're going to come from this space curve. They say we want the tangent line to the curve, so going around like this. And so at the point 0, 2, 1, look, you're half done. 0, 2, 1, there's your point on the line that you're trying to write. And then how are we going to, so here's 0, 2, 1, say right here. How are we going to get how are we going to get the direction vector? So the point we've got, 0, 2, 1. And now we need a direction vector. And that direction vector, what is going to be such that we get a line, so it's parallel to the tangent to the curve? Ezra.
Plug in the points, the x, y, and z, figure out where they coincide, and then you take the derivative of those, and you plug in that t value that you got into the derivative.
Oh, so use this point to figure out what t we have.
Yes.
Right. So we need to know what t we have. So 0, 2, 1 is going to be t equals either 1 or -1. Which one is it? be either, right?
You plug in 1 into the z though, it only gives you positive 1.
No, I got z equals t to the 4th.
It could be negative 1.
Yeah, could be 1 or negative 1. But anyway, once you have the t value, I don't want to get bogged down on that. Once you have the t value, suppose we'll just say it's 1. Okay? Once you have the t value, now I got to get this direction vector. So that's what? That's the direction the curve is going at 0, 2, 1. So what do I need? Derivative. Do I need the tangent? Do I need the unit vector? No, because I'm writing the equation of the line. Any vector parallel to this line is good enough. So I can use r prime of 1. R prime of 1 will be the direction of the curve. It won't be unit length, but it doesn't matter. So r prime of 1 will be the direction of the curve, so it'll be my direction vector for my line. So I got the point, 0, 2, 1. The direction vector will just be the derivative vector evaluated at the t in question. Boom, done. Then I just use what we learned before and set up the equation of the line. Okay, we need to start new stuff. Any questions? So today in recitation, if you want to tell Key that at the beginning, if you want to do 1 or 2 more web work problems that were due today, you guys can work on those. That's fine. If there's still questions on web work. Can we start new stuff? Are we good? All right, we got a cool day today. This is cool stuff today. But you may think that's also harder, too. So let's start with, can you sketch this curve? And then what surface does it lie on? Now, when I ask that question, I'm not asking for what 2 surfaces intersect to form this curve. I'm not asking that. Because actually that doesn't exist. And that was, I think, a question you had Tuesday's recitation. All I'm asking for is a single surface that this curve is always on. I'm not asking for 2 surfaces whose intersection give you this curve, because that doesn't exist. Right? What is it in y and z? What's going on in y and z? Ellipse, right? So you have an ellipse in y and z, and then as t increases, yeah, so it's going to go around an ellipse in y and z, and then what? As t increases, come out at you, right? So what will that form? Elliptical spiral. Why not? Okay, now I have 3 vectors there, a black, a blue, and a red. Can you see the difference between the colors? If you can't, ask somebody, ask me, but there's a blue vector, a red vector, and a black vector. I want you to identify each by color and then find the vector function for each of those. So there's a black, a blue, and a red. Identify each by color. So the blue vector is what? And then the red vector is what? And the black vector is what? Yep, and then find them. Find those functions. Find those functions. Okay, what's the blue vector? The blue is just RT. That's the given, that's what I gave you, right? That's this. Should it identify the blue vector as just this, right? That's that vector function. Yes, if this was time and this is a particle going through space, then it's position. Doesn't have to be, right? So that's a very common application of these space curves, but doesn't have to be motion through space. It could be something else also. All right, but yes, it's very helpful to think of it as motion through space. Okay, so then the black and the red, one of those two is what? The derivative, right? The derivative. But do we know which one is which?
Yes.
Black is
Red is the derivative because it's changing. So black would be the unit.
All right, so they're actually both maintaining the same. They actually both maintain the same magnitude. They just change direction. So you really don't know until we do it which is r prime of t. So what is r prime of t? 1, -2 sine t, and now, what is the magnitude of that? It says bigger or less than 1. So the magnitude of that is square root of 1 plus 2 sine squared. 4, I was just testing you. Plus, okay. So we know that sine squared plus cosine squared is, now I have 4 sine squared t plus cosine squared plus 1, and then square root, but that doesn't matter. So, is this bigger or smaller than 1? It's bigger than 1. Therefore, which one of these is r prime of t? Red, or they're coming into view now? Red or black? Red has to be the derivative because its magnitude is bigger than 1. And then we assume that black is the unit version of that, but because it's the only thing left that it could be. We learned about that last time. So the red one is the derivative, r prime, and the black one is what we called last time. So red. So blue is that. Yeah, I shouldn't have put this on the sheet. You guys are all freaked out about what to write in your sheet, right? Don't worry about that. Make sure you learn what we're talking about. Okay? So red is going to be the derivative, and then the black one is unit tangent. What's the symbol for that? What did we say? Capital T. Capital T. And to get that, it would be, just as a review of last time, the unit tangent vector is the unitized version of the derivative. So you would take the derivative vector, divide by magnitude. Okay, so that's review from last time, just kind of putting you on the spot to see if you can identify things visually. Any questions on that? Okay, so any questions? All right. So let's say we have a curve like this. And this is some vector function in space. And we're going to look at a particular t value, say right here. So we just talked about the unit tangent vector. It points in the direction of what? Increasing t. So as little t increases, it's the direction that point is moving along the curve, right? So it's tangent to the curve. So there's another, so that's called the unit tangent. So what would, if we took the derivative of that and made it a unit vector? What would give us that? So what's the magnitude of t? 1. And it's always 1. For all little t, it stays magnitude 1. So we're talking about the rate of change, a rate of change of t, and its magnitude is always 1. Then what does that rate of change have to do with? Direction only, right? If it's maintaining a magnitude of 1, then the rate of change of capital T has to be talking about the direction. So suppose, like at that example right there, we had, so say that point is for t equals 3, okay? So if I took, this would be t of 3, and then what would, say, t of 3.01 be? What direction would it be? Steeper or more shallow? No, so now I'm going to take t of 3.01. Is capital T going to be steeper or more shallow? More shallow, right? Because it's bending down here, right? So if I put t of 3.01 like this, it's going to look like that. So if we're talking about the rate of change, we're talking about like how much change between that vector, this first vector to the next vector, or the difference, right? It's kind of like this one minus this one per unit of little t. So what vector would that be? It would be like this, right? So if that change in little t was very, very small, do you see that the direction of this would be what? It would be the direction of turning, right? It'd be the direction of, it's like the direction of turning. And how would it relate to capital T? So how, if this was a really small, so if these were really close together, then that resulting vector that's like showing the change of capital T over a small interval of little t would be like what? Wouldn't it be orthogonal to capital T? It's showing the direction of turning, which is what? Down to the right. We're turning down to the right now. So we're going to get a unit vector like this. Does it make sense? So the rate of change of capital T, or capital T prime, is the rate of change is like, and then normalized, it's just telling us the direction of turning. And the direction of turning now is we're clockwise, right? If we're turning clockwise, then at that moment we're turning this way. See that? Because we're turning clockwise. All right, so that thing is called the unit normal vector, because it's normal to the curve. The unit normal vector is normal to the curve, and it gives the direction of turning. Right? Do you see that at this moment we're turning down and to the right, or we're turning clockwise? So what direction of turning is that? That's this way. Does that make sense? Okay, so then there's a third vector, which is called the binormal vector, which is also a unit vector. And we get, so this is how we get the normal vector. It's the unitized version of the derivative of the unit tangent. And then if we do t cross n, we get this thing called the binormal vector. And so if it's t cross n, then based on my sketch up there, can you determine, that'll be another unit vector, can you determine what's the orientation of that vector? Can you figure it out? If it's t cross n. Coming right out at us. Not quite.
It's going to be our
Remember, so T, you point your finger, right hand rule, point your fingers in the direction, get your hand, point the direction of T so that you can curl your fingers towards N, which means like this, into the board. If that plane is parallel to the board. Sorry, if that curve is kind of parallel to the YZ plane. So like this. So everything is orthogonal. So what you get is you get a little three-dimensional space, like a little three-dimensional coordinate system that moves along with the curve as little t changes. Where capital T is always pointing what? Direction of the curve. N is always pointing the direction of turning. Okay? And then B is orthogonal to those two. B is orthogonal to those two. That's called the binormal vector. Okay, so the way you can remember if it's T cross N versus N cross T is just think of the word ton. Why? Because calculating the binormal vector is a ton of work. Because just getting the normal vector so this is even crazy long algebra. To first get T, take the derivative of it, and then unitize it. It's ugly most of the time. Very ugly. Okay? So now you got to take that one and you got to do the cross product with your tangent vector. So it's a lot of algebra. So, and I'm not going to be interested. Maybe having you do just that one time or something. But these principles of the orientation of the vectors versus the curve is much more important to me. That you understand what they're about. So questions on that. So then, this little three-dimensional coordinate system that's moving in space with the curve also forms three planes. Three planes, okay? One of those planes is, so we're going to write this down in a second. Let's just talk it through first. One of those, the easiest plane is the plane that's normal to the curve, right? So it's like the curve is passing through this plane orthogonally. So which two vectors would form the plane that's orthogonal to the curve? Of B, T, and N, which two would form the normal, what we call the normal plane? T and N form the normal plane. Agree with that? No? She wants B and N. B and N, right? B and N form the plane. So if you see that plane, right, like that this curve is normal to, or orthogonal to. So then to write the equation of that plane, which vector would you use? Right? What vector gives us the orientation of a plane? The normal vector, okay? So the vector is the vector formed by B and N, but to write the equation of that plane, the normal plane, we would use the vector T, not N, right? The normal vector is one of the vectors parallel to the plane. The vector we'd use to write the equation of the normal plane would be T. Do you see that? Does that make sense? Okay, next plane, the tangent plane. So there's a plane that the curve comes and is tangent to at that point. That would be formed by which two vectors? B and T. B and T would be your tangent plane that comes up and ends tangent. And so to write the equation of the tangent plane, we use T, right? We use N. Okay? So just because it's the tangent vector, If we're going to write the equation of the tangent plane, we need the orthogonal vector to that plane, which is n. Do you see it? Finally, there's one more plane. That's the plane of t and n. So how would we describe the plane of t and n relative to that curve? Yeah.
We use it with BT, which is orthogonal to TNN.
Okay. My question is, the vector, the plane formed by t and n, how is it related to the curve? How do we see the relationship between the curve and it? Yeah, it's kind of like a parallel plane, or it's like the plane that the curve is in at that moment. Do you see that? It's the plane that the curve is actually in at that moment. T and n. That's called the osculating plane. We're going to write this all down in a second. Okay, it's called the osculating plane, and its orthogonal vector is B. You would use B to write the equation of the osculating plane, which is the plane that the curve is in. Any questions? So let's write all that down. Okay, let's write all that down. So we had we did the normal plane first, and then we had a tangent plane, and then we had osculating plane. So for each of those planes, we've got, what is its relation to the curve? So what is the normal plane's relation to the curve? That's an easy one. Normal to the curve, right? Okay. What are the two vectors that form that plane, or the two vectors that are parallel to that plane? Do you remember? B and N. B and N. So then the vector you'd use in the plane equation for the normal plane? T. Which makes sense. The direction of the curve is T. The normal plane is going to be orthogonal to that direction of that curve. Okay, the tangent plane is tangent to the curve. Two vectors that form that plane. What did we say? B and T. Was that B and T? So the vector used to write that plane equation? N. Or any vector parallel to n. You can write the tangent plane. Finally, the osculating plane. We said that's the plane, yeah, parallel to the curve. Like the plane the curve is kind of in at that moment, or parallel to the direction of motion. It's made up by N and T. And the osculating plane we write with a binormal vector because it's orthogonal. So make sure you don't just memorize all these words, but it makes sense with the image that I drew in the previous screen. Okay, so let's practice this. So I'll give you a second to write it down. Are we good? Okay, so let's look at that same example again. A different one here. So here it is in action, right? So you've got this three-dimensional coordinate system that's moving along with the curve. So at any given value of t, you've got the unit tangent vector, unit normal vector, and then the binormal vector. So first task, identify which is which by color. Okay, identify which is which by color. Sure. Yep. Why is that such a pain? Why all the size when we put something on a blue sheet? You want to learn, right?
Yes.
Yes, you want to learn. So you got to think and work at it. So there's black, purple, red, and blue. Pink?
Are we labeling the plane or are we labeling?
No, just the vectors first.
Okay.
How's that? Did the colors show up good there? How about right there? There you go. And I'll give it a... There's a good view. Sorry.
The purple one is the one from the origin?
Yeah, this is purple here. Or pink.
But black's it's always facing the direction.
That's a pretty good view right there. No. Jenny Lou.
I try to get set up.
Alexandra Pippin. Alexandra.
What's that?
Rachel.
What color is that?
Rachel.
The one that points like that?
This is purple, red, black, red, blue.
Black, red. I'm not too colorful. Red.
G. See what.
Yeah, I see. This is that purple. This is purple.
So, which one's pointing in the direction of change? Or, no, sorry, direction of the curve.
Red.
That's a bad view. Which one's pointing in the direction of the curve? Red. So it's the tangent. Which one's pointing in the direction of turning the direction that we're turning at the moment?
Black.
Black. So it's pointing to the center of the curve, right? It's pointing into the center of the curve. That only leaves one more thing. Right, so do you see that the blue one then is what? Orthogonal to the plane that the curve is in at that moment. See that? So if the plane the curve is in at that moment is right here like this, right there at that moment it's in this plane, the blue is orthogonal to that one. Okay, so now let's actually get these at a couple points. Now notice I changed this up a little bit. You get the same general space curve, but now I'm letting y be 2 sine t and z be negative cosine t. I think that's different than what I had before. That's okay. So let's look at 0. Okay. So at little t equals 0. Can we deduce what these three vectors are? So one of them is easy. Which one do we know right off the bat? So this is at t equals 0. So at t equals 0. So we can write down what the point is on the curve, right? The point on the curve would just be 0, 0, negative 1. That would be from our vector function. And that's which color? Pink or purple, right? Pink or purple. And so then which one of those can we just write down? Black, which was which one again? The normal, right? So the normal to the curve then was going to be pointing in the direction kind of the center of rotation, right? So that's just going to simply be what? We can just write it down. N of 0 is had 0, 0, 0 and 0, 0, negative 1. 0, 0, 1. 0, 0, 1. Okay? So now, what about our unit tangent vector at 0 and our binormal at 0? So if we look straight down on what's happening here, maybe. Whoa. There we go. I'm looking straight down here, but the x-axis is to the what? X-axis to the left, y-axis is down. Come on. Good enough. So the unit tangent, I think we're going to have to do a little math here. So how can I find the unit tangent? What should I do? Take the derivative of our vector function, right? And then we need a unit vector in that direction at 0. So r prime is 1, 2 cosine t, and sine t. So at 0, we get 1, 2, 0. So there's only one thing left to do, which would be what? We got the direction of that red vector, which is the tangent, unit tangent. Just make it into a unit vector. So it's a lot easier to do these if you have a particular point, right? It's when you have to do them as functions when the algebra gets really ugly, okay? When you have to do all these derivatives and normalizing and maintaining expressions in terms of little t, that's when things get ugly, okay? So, but all we need to do to get t of 0 is just unitize this vector, which is is it square root of 5?
Yeah.
Okay, so now, what do we know? So we know that the blue one, to get b of 0, we know that it's what? No, but more simply than that. It's just orthogonal to this, right? It's orthogonal to this. And it's, what is its x? Is this x going to be positive or negative? No, this is actually positive x this way and positive y down here. So it's going to have a positive x component and a negative y component. And we know that what? The dot product would have to be 0 between t and b. So we can write it down, right? So can you write down? So see, here, the x component of this one is 1 radical 5, and the y component is 2 radical 5. Since they're orthogonal, then what about the x component of this one? So you can use symmetry here, is what I'm saying. So x component of the red vector is 1 over radical 5. Y component is 2 over radical 5. But now, because this is orthogonal, we know exactly what it is now. This is orthogonal to this. So its x component is 2 radical 5, and its y component is 1, but we got to get the dot products to be 0, right? So we set a positive x and a negative y. So positive x and a negative y. And now is the dot product 0? So did you see that logic there? That's something that may come up again. So I want to do that. So if you've got a vector and you want one orthogonal to it, like this, but you're just talking about 2 dimensions, you're going to switch components, right? You're going to switch components and make sure the signs are right. This one orthogonal to this means its x component is the same as this one's y magnitude, and this one's y magnitude is the same as this one's x magnitude. This one has positive x and negative y. There it is. And now the dot product, you can just check it. T0 dot B0 should be 0 because they're orthogonal. And we do. We get 2 over 5 minus 2 over 5 equals 0. So you may see that come up again. It's just a kind of a shortcut to getting an orthogonal vector in 2 dimensions. Change the components, reverse the components, and get your signs right so that the dot product is 0. Yeah.
You just have to do it out if there's all 3 components used.
Now, yeah, if you're in truly in 3 space, yeah, then this is just a trick for two dimensions. Just a trick for 2 dimensions. Okay, so I want you to do it for t equals pi over 2, and I'll put it there. So you're going to do the same thing for pi over 2. Which is this big black point right here. So I'm going to set it on pi over 2. So this is a lot more about using intuition and understanding things spatially than it is doing a lot of algebra, okay? Kind of like what we just did. So if I can maybe get this thing spinning really slow. So this is t equals pi over 2. Find t of pi over 2, n of pi over 2, and b of pi over 2. And then maybe better is if I give you one. So I'll give you this view for a minute, and then I'll give you another view for another minute, okay? Pretty easy. Just looking straight down on it to help you with the black one. X here, Y here, right? Positive X, positive Y. All right, and then here's looking at it this way. Looking at the XZ plane. I'll leave it there. This is positive Z here. Positive X this way. Positive Y coming out at you. Use symmetry. Use symmetry. So this is out the far right side of the far right side of the curve. The far right side of the curve at that moment. So imagine what's going to happen at the far right side, right there.
Yeah.
So for your R, your standards, for the T, it's 1, 0. Because your normal is just
That's a pretty good view.
yes. My normal I got.
So your red vector is
1, 0, 1.
no, but it's a okay. Yep, that's the right idea. But it's the unit tangent, right? Unit tangent,
1 over root 2, 0.
right? It's going in the positive x direction, and it's going up, but it's parallel to the xz plane, so it's y component 0. Did anybody get that before I did it? Lots of you. Good. Okay, good. And finally, so what we have left is binormal vector. Oh, the normal vector, that should be really easy. You just write that down. Right, because we're out here at the right side. Just, I gave you that top view. You see that it's what? Parallel to the xz plane. It's pointing right in the direction into the center of the ellipse. So you just write it down. What unit vector is that? 0, negative 1, 0. Just pointing right in the negative y direction. Do you see it? The black one. Okay, and then the binormal. We're going to get that using the tangent. So we're going to take a look at it and use that technique I showed you. So here's positive x and z. Binormal has, is it positive or negative x and positive or negative z? Positive x, negative z, and we know its dot product with t would have to be 0, right? You finish it, right? So you know that t is up and to the right, positive x, positive z, equal magnitudes components. You finish it. I won't write this one out. This is for you. So what is the components of P? That's the blue one. Very nice symmetry on that one, right? Because it's right there at the greatest y value on the curve out there. So you have all this symmetry to it. Okay, so, and then we could have talked about writing the equations of those planes at this point. But if you have the point and you have the vectors, then you just use the equation of the plane to write down each of those planes. Okay, anybody have a question? Don't be afraid to ask. I know that seeing it for the first time can be confusing.
How would you find the normal vector if you didn't have, if it wasn't just like obvious like this?
Yeah, so if it was truly arbitrary, you had no visual cues, then you'd have to take the it's the normalized derivative of the unit tangent. You get the unit tangent vector function in terms of little t. You'd have to take the derivative of that in terms of t, find the magnitude of that in terms of t, and set up it's gross. Right, it's gross. But it's just knowing your derivatives and pushing the symbols. Okay, let's do one more thing. So there's any more questions about this? All right, I'm gonna talk about one more thing? Okay, so I'm still going to talk about one more thing, but just I know that this is confusing, especially the first time you've seen it. So get into my office and let's have conversations about it. That's how it's really going to. If you can ask your own personal questions about what you don't understand, that's how you're going to get better. So come into office hours and we'll talk through all this stuff again. All right. One more thing here. So with this comes an idea called an osculating circle. So here's an R2. Okay, so given any point on a curve, there is a circle that's like the tangent circle. Okay, so it's tangent to the curve, and then it has the same what's called curvature of the curve at that point. So where does this function f 16x cubed minus x squared, where does it have the highest curvature? Where does it have the highest curvature? At the local max and min. Do you see that at the origin there? And this local min, the graph has the highest curvature. So then what does that mean for this thing called the oscillating circle? What about it? At the places where the curvature is the highest, it's the smallest circle, because the smaller your circle is, the higher the curvature is in that circle. The bigger a circle is, the lower the curvature, right? So out here where this curve is relatively flat, you have the oscillating circle is really big because you're going to have a circle that has low curvature, a big circle. But then when the curve has high curvature, like tight turning, you're going to have your oscillating circle is going to be very small because small circles have high curvature. Okay, so I just want to write down what the curvature is, kappa. So it's kappa of t. And the amount of curvature is how much turning per speed of the curve, right? So this is like, what is that? So it's like the magnitude of turning, right? Magnitude of turning would be t prime. Per, what's that? That's like velocity or amount of curve swept out, right? Amount of curve swept out. So do you see how that ratio then will give you how much curvature you have, right? So the magnitude of turning with respect to how much curve is swept out will give you this thing called curvature. It's this value of curvature. So that's a scalar. That's a scalar. But it's a function of where you are on the curve. Okay, we got to stop there. So we'll pick it up there Tuesday. Like I said, in recitation, if you guys want to tell P it's okay to spend the first 10, 15 minutes